Next page. Let's find the equation of the tangent line to the curve at x is equal to 0. All right, that's going to be for part A. So for part A, of course, we know that y minus y0 equals mx minus x0 is the equation we're looking for. Because we're told that x is equal to 0, right? Then we know that's our x naught. And we can find our y0 by plugging into the equation, right? So y0 is f of 0, right? Because that's our x value, which is going to be minus 3 cubed times 1, which is minus 27. Now we just need to find m. And how do we find m? We know m is found by the derivative. It's going to be f prime of x, right? When we evaluate it at x equals 0. Okay, so this is going to be equal to, well, we got to use the product rule. So I'll just write product rule. Okay. F is equal to 4x minus 3 cubed. G is x squared plus 1 squared. F prime is 4x minus 3 squared times 4. G prime is 2x squared plus 1 times 2x. All right. Now that means that our derivative f prime g plus g prime f. So that's going to be 12 4x minus 3 quantity squared x squared plus 1 squared plus 4x x squared plus 1 4x minus 3 cubed. We're going to plug in a 0 for x and then see what we get as our m. So it's going to be f prime of 0. It's going to be 12 minus 3 squared times 1 plus 0, 0, 0, 0, right? So it's basically 9 times 12, which is 90 plus 18, 108. Okay, so our equation of the line for this one is going to be y minus 27 is equal to 108 times x minus 0. Okay, which you can that way, but it's a 0, so we could go ahead and simplify. All right, so that's it for that one. Let me erase and then do the next one. For this one, we're given x is equal to negative pi over 4. And y is equal to 0. Right, so those are x naught, y naught. We just need to find y prime. Clearly, from what's going on here, we're going to need to use implicit differentiation. So we'll ddx both sides. Okay. Left-hand side, we're going to use the product rule. Left-hand side, we're going to use the product rule, right? So f prime g is going to be 2x times y, okay? Plus g prime f is going to be plus x squared y prime, right? Derivative of tangent is secant squared, and then that's going to be 0, right? So we get y prime is equal to secant squared x minus 2xy divided by x squared. Okay, when we plug in the negative pi over 4, we get secant squared negative pi over 4 minus 2x is negative pi over 4, y is 0, divided by negative pi over 4 squared. Okay, but negative pi over 4 is in the fourth quadrant. It is 45 degrees in the fourth quadrant. Cosine and secant are positive. It's a reciprocal of the square of cosine, which is 1 over radical 2. Reciprocal, radical 2 squared, 2. Okay, minus 0 over pi over 4 squared. And so this ends up being equal to 32 over pi squared. Okay, so in this context, we have y minus 0 is equal to 32 over pi squared. times x minus pi over 4 minus plus. Alrighty, let's keep going. Number 5, we're looking at L'Hopital's rule, most likely. How we know? DSP. When I plug in 0 for x, I get 0. I plug in 0 or I approach 0 for ln, we know it's negative infinity, right? So this is definitely a L'Hopital situation. So we have to decide how to use L'Hopital, and L'Hopital only works for quotients. So what are we going to bring down, the ln or the power? Definitely the power, not the ln. Okay. When we do this, we get infinity over infinity. So we'll get limit x approaches 0 from the right, 1 over x over minus 2x and minus 3. That's going to be equal to the limit x approaches 0 from the right of x squared over negative 2, which is 0. All right. You can definitely graph it in a calculator and verify that is the case. Next one. This limit, as we plug in infinity, is going to be e to the 1 over infinity, which is e to the 0, which is 1, minus infinity over infinity. So we get infinity over infinity, right? So that's definitely another L'Hopital situation. In this case, no need for algebra before we proceed. So using L'Hopital, we got to use a chain rule, right? So derivative of any e is the same thing. But that negative 1 over x is complicated, so we got to take the derivative of it. Let's do some side work. 1 over x negative, okay, is d dx, just like we saw on the first page. Negative x to the minus 1. That's x to the minus 2, okay? So I'll put an x to the minus 2 over here from that chain rule derivative. Minus 1 over 1. All right, so now when we take the limit, we get the limit as x approaches infinity of e okay, so now when we DSP this, we get an e to the minus 1 over x, which again, as x goes to infinity, that is like e to the 0, so that's 1. And then x to the minus 2 is dividing by infinity, right? So that first term is going towards 0. So that's going to be 0 minus 1 over 1, which is negative 1. Okay? And then the final one, we're looking at the limit as x goes to infinity of this expression. Let's DSP it. And we end up with infinity raised to the 3 over infinity, which is 0. Infinity to the 0 is an indeterminate power. And so we have to use this little trick where we said, okay, if we want to find the limit as x goes to infinity of this, because it's a power, we have to use ln, right? This is going to end up being e. Okay, so exp means I'm going to raise it to the e power of the limit as x goes to infinity of the ln of that whole thing. Okay. All right, so this means let's first of all focus in on this part on the inside. Find that limit. We get our answer and just raise it to the e power, and then we'll be done. Okay, or I should say raise e to that power, then we'll be done. All right, so let's see. We're going to end up with ln, I should say lim. We'll end up with the limit as x goes to infinity. Now, what happens when we use ln? Ln brings down the 3 over x, right? So it's going to be 3 over x, ln of 1 plus x. Okay, we plug in the infinity, and we clearly get an infinity over infinity in this case, right? If you're more comfortable, we could write it as bring out the 3, limit x goes to infinity, ln of 1 plus x over x. Okay, but it kind of looks like the first situation we dealt with, where we have a ln and a power. Things are situated where they need to be right now, so let's keep it moving. I'm just going to be with L'Hopital's rule, 3 times the limit x goes to infinity of 1 over 1 plus x times 1 over 1. Okay, which is simply going to be as x goes to infinity, 1 over 1 plus x goes to 0. Right, so that's going to be nothing but a 0, right? So our final answer then is going to be limit x goes to infinity of the whole thing will be e to the 0, which is 1. All right, so we want to take a look at this at Desmos. Do not look on the left-hand side. Just don't worry about that. What we have here is the function, and you can see that it's approaching 1 as you go towards infinity. This keeps going. All right. Okay, next question. Liquid is being poured into a cylinder at a radius 2 centimeters at a rate of that. At what rate is the height of liquid increasing when the volume is 16 centimeters? So we have to remember that the volume of a cylinder that looks like this with height h, radius r, is pi r squared h. So we want to know the rate at which the height is increasing when the volume is equal to that, and the volume is increasing as well. All right, so the radius actually is going to be staying the same for the cylinder, but the height is going to be continuing. Just imagine pouring water in a Coke can, and the radius isn't increasing, but the height of the water is as the volume increases. So height is a function of time, right? Whereas radius is not. Okay. And so our dV dt, which is the rate of change of the volume, is going to be ddt of pi r squared h, which is pi r squared d dt of h, right? Because we can just pull out the constants, which is pi r squared dh dt. Okay, so what do we know? We know that dV dt is the cubic centimeter change, right? So that's going to be 3.7. Worry about the units later. We know that the radius is 2, right? So that's going to be a 2 right there. And what we want to know is at what rate is the height of the liquid changing, right? So that's dH dt. Okay, so we need to solve for dH dt. dH dt is going to be dV dt divided by pi r squared. 3.7 divided by 4 pi. And that's going to be in centimeters per second. All right, we'll leave it at that. Last question on this page. State the behavior of the exponential natural log functions. And no need to show work. So they're just asking you to identify what these functions do. These are very important concepts, especially as you move into calculus 2. Just understand and know what these functions do. Okay, so as far as the natural log function, we can fire up Desmos again and see what it does. And that's how I recommend doing this problem. Just strictly going to Desmos and just graphing it. Okay. Okay, so ln of x, we see what it looks like, right? It looks like it has potentially has a horizontal asymptote. You know that it doesn't. It just increases to infinity slowly. But it does have a vertical asymptote at the y-axis. It crosses the x-axis at x equals 1. All right, and so let's go ahead and see what we're asked to identify. Okay, and so we have that the horizontal asymptote is none. Vertical asymptote x equals 0. X-intercept is x equals 1. Y-intercept none, right? Since it has a vertical asymptote at the y-axis, right? Looking at the e to the x function. Right, so it does the opposite things. It has a y-intercept at 1 instead of x-intercept at 1, right? It has a horizontal asymptote instead of vertical asymptote at x equals 0 instead of y is equal to 0. It looks like it's going slowly and has a vertical asymptote, but it doesn't. It increases slowly to infinity, right, as x goes to infinity. So as we remember, they are inverse functions, right? So they look like reflected across the line y is equal to x. They're inverse functions. So what one does on the x level, the other one does on the y level, right? So that's what we're talking about here. Horizontal asymptote, we have y is equal to 0. Vertical asymptote, none. X-intercept, none. Y-intercept, y is equal to 1. Right? So a mirror image of each other.